There may be another Earth out there. Not just another planet, not just a distant rock orbiting a star, but a world with oceans, clouds, weather, chemistry, and maybe even life. For most of human history, that idea belonged to imagination. We looked up at the night sky and wondered whether the stars were only lights in the darkness, or whether some of them were suns with planets of their own. Today, that question is no longer science fiction. Here on Infinite Science, we are entering one of the most important chapters in modern astronomy, the serious hunt for Earth 2.0. NASA has now confirmed more than 6,000 planets beyond our solar system. These worlds are called exoplanets, and they have completely changed how scientists see the universe. Some are giant gas planets orbiting dangerously close to their stars. Some are frozen worlds drifting in darkness. Some are scorched lava planets where rock may rain from the sky. Others may be rocky, temperate, and possibly similar in size to Earth. But somewhere in this growing catalog, scientists are searching for something extraordinary. A planet that is not too hot, not too cold, not too large, not too small. A world with the right kind of star, the right orbit, the right atmosphere, and maybe the right conditions for liquid water. A world that could force humanity to ask the biggest question in science. Are we alone? After the first confirmed discoveries, the number of known exoplanets began to grow quickly. Telescopes became more powerful. Computers became better at analyzing tiny signals. Space missions were designed specifically to search for planets around other stars. And slowly, what once seemed rare became common. Planets were everywhere. The Milky Way was not just a galaxy of stars, it was a galaxy of worlds. But finding a planet around another star is incredibly difficult. Stars are bright, planets are faint. Trying to detect an Earth-like planet beside a Sun-like star is like trying to spot a tiny speck of dust next to a blinding spotlight from miles away. So scientists had to become cosmic detectives. One of the most successful techniques is called the transit method. When a planet passes in front of its star from our point of view, it blocks a tiny amount of starlight. The star appears to dim, just slightly for a short time. That tiny dip can reveal that a planet is there. If the dip repeats on a regular schedule, scientists can estimate the planet's orbit. The depth of the dip can reveal the planet's size. The timing can help show how close it is to its star. This method helped missions like Kepler and TESS discover thousands of possible planets. But there is a catch. The planet's orbit has to line up just right from Earth's perspective. If it does not pass in front of its star from our view, we may never see the transit at all. Another method is radial velocity. A planet's gravity pulls on its star, making the star wobble slightly. By studying tiny shifts in the star's light, scientists can detect planets that cannot be seen directly. Together, these methods have built a new picture of the galaxy. Planets are not rare accidents. They appear to be a natural part of star formation. Where stars form, planets often form too. But the real challenge is not just finding planets, it is finding the right kind of planet. When people say Earth 2.0, they often imagine a blue world with oceans, clouds, and maybe green continents. But scientists have to be careful with that phrase. No confirmed exoplanet has been proven to be a true second Earth. A planet can be Earth-sized without being Earth-like. It could have no atmosphere. It could be blasted by radiation. It could orbit in the habitable zone but still be frozen, toxic, or dead. The search for Earth 2.0 is really the search for a complete set of conditions. Size matters. A planet much larger than Earth may hold on to a thick atmosphere of hydrogen and helium, making it more like a mini Neptune than a rocky planet. A planet too small may not keep its atmosphere for billions of years. Orbit matters too. If a planet orbits too close to its star, water may boil away. If it orbits too far, water may freeze solid. This leads to the famous idea of the habitable zone.
The habitable zone is the region around a star where temperatures could allow liquid water to exist on a planet's surface, assuming the planet has the right atmosphere. But the habitable zone is not a guarantee of life, it is only a starting point. Venus is close to the inner edge of our Sun's habitable zone, but its thick atmosphere created a runaway greenhouse effect. Mars sits near the outer edge, but today it is cold, dry, and thin-aired. Earth is not habitable simply because of its distance from the Sun. Earth is habitable because of a delicate combination of factors: atmosphere, oceans, geology, chemistry, climate stability, and time. That is why the next stage of exoplanet science is not just counting planets, it is studying them. Scientists want to know what these worlds are made of. They want to know whether they have atmospheres. They want to know what gases exist in those atmospheres. They want to know whether the chemistry looks ordinary or whether it hints at something more. This is where powerful telescopes become essential. When a planet passes in front of its star, a tiny amount of starlight can pass through the planet's atmosphere. Different gases absorb different colors of light. By studying that light, scientists can search for molecules like water vapor, carbon dioxide, methane, and oxygen. This technique is called transmission spectroscopy. It is one of the most promising tools in the search for life beyond Earth, but it is also extremely difficult. The signals are tiny, the planets are far away, the atmospheres are complex, and chemistry can be misleading. A gas that is produced by life on Earth might be produced by non-living processes somewhere else. That is why scientists do not look for one magic molecule, they look for patterns. For example, oxygen and methane together would be interesting because they react with each other. If both existed in large amounts in a planet's atmosphere, scientists would ask what process is constantly replacing them. On Earth, life plays a major role in shaping the atmosphere. Plants, algae, microbes, oceans, volcanoes, rocks, and sunlight all interact in a planetary scale system. From far away, Earth would not just look like a random ball of rock, it would look chemically active. That is what scientists hope to detect elsewhere. Not proof from a single signal, but a planetary fingerprint. Still, the search for life must be careful. A possible biosignature is not the same as proof of life. The first real evidence of life beyond Earth would be one of the greatest discoveries in history, so the evidence must be extremely strong. A signal would need to be checked, rechecked, and tested against other explanations. Scientists would need to rule out geology, radiation, clouds, instrument errors, and unusual chemistry. Science does not jump from interesting signal to alien life overnight. It builds the case slowly. And that is exactly why the hunt is getting serious. The first era of exoplanet science asked, are there planets around other stars? The answer was yes. The second era asked, what kinds of planets exist? The answer was almost everything imaginable. Now we are entering the third era. Which planets can we truly understand? Which ones are rocky? Which ones have atmospheres? Which ones have water? Which ones might be habitable? And which ones could show signs of life? Future missions are being designed with these questions in mind. NASA's Nancy Grace Roman Space Telescope is expected to expand our understanding of exoplanets, especially through microlensing and direct imaging technology demonstrations. Roman could help reveal planets that current missions miss, including worlds farther from their stars. It will also help scientists understand how common different types of planetary systems are across the galaxy. That matters because finding Earth 2.0 is not just about finding one planet. It is about understanding where to look. Then there is the proposed Habitable Worlds Observatory. This future mission concept is aimed at one of the most ambitious goals in astronomy, directly studying Earth-like planets around nearby stars and searching their atmospheres for possible signs of life. If built, it would represent a major leap. It would not just ask whether a planet exists, it would ask what kind of world it is. Does it have an atmosphere?
Does it show signs of water? Does it contain oxygen, methane, carbon dioxide, or other important gases? Does its chemistry look like a dead planet shaped only by geology? Or does something seem out of balance? This is the frontier. But Earth 2.0 may not look exactly like Earth. Some potentially habitable planets may orbit red dwarf stars. These stars are smaller and cooler than the Sun, and they are the most common stars in the galaxy. That makes them tempting targets. But red dwarfs can also be violent. They may release powerful flares. A planet close enough to be warm may also be exposed to intense radiation. Many such planets may be tidally locked, with one side always facing the star and the other side trapped in darkness. At first, that sounds impossible for life, but some climate models suggest that if the planet has the right atmosphere, heat could move around the globe. The day side could be warm, the night side cold, and the region between them potentially stable. Life, if it exists, may adapt to conditions very different from Earth. Still, Earth remains the standard. Earth has had liquid water for billions of years. It has a protective atmosphere. It has long-term geological cycles. It has a stable star. And it has life that transformed the planet itself. Finding all of that somewhere else will not be easy. But the search is more focused than ever. Scientists are building target lists of nearby stars. They are identifying small rocky planets. They are improving atmospheric models. They are designing instruments that can separate the light of a planet from the glare of its star. Every discovery narrows the search. Every strange planet expands what scientists think is possible. And the numbers are powerful. The Milky Way contains hundreds of billions of stars. If planets are common, then the number of worlds in our galaxy could be enormous. Even if Earth-like conditions are rare, rare does not mean impossible. The question is no longer whether planets exist. The question is how many of them have the right conditions. And beyond that, how many made the leap from chemistry to biology? That leap remains one of the deepest mysteries in science. How did life begin on Earth? Was it an almost impossible accident? Or does life emerge naturally when the conditions are right? If scientists find life on another world, even simple microbial life, it would transform our understanding of the universe. It would mean biology is not just a local event. It would mean life belongs to the cosmos. For now, we do not know. There is no confirmed evidence of life beyond Earth. No confirmed Earth twin. No proven second biosphere. But what we do have is a rapidly growing map of possibility. More than 6,000 confirmed exoplanets, thousands more candidates waiting for confirmation, more powerful telescopes, better detection methods, more precise atmospheric studies, and a scientific community moving from discovery to investigation. The hunt for Earth 2.0 is no longer just a dream. It is becoming a structured, scientific search. A search with targets, a search with instruments, a search with data. A search that may one day give humanity an answer to a question older than science itself. Somewhere out there, orbiting an ordinary star, there may be a planet with clouds moving across alien oceans. There may be rain falling on distant rocks. There may be chemistry unfolding in warm seas. There may be life too, small to see, but powerful enough to change an atmosphere. Or maybe Earth is rarer than we ever imagined. Either answer would be profound. If we find another living world, we learn that life belongs to the universe. If we do not, we learn just how precious Earth truly is. The hunt for Earth 2.0 is really a mirror. It tells us what we are searching for out there, but it also reminds us what we already have here. A living planet, a fragile atmosphere, a world filled with oceans, forests, storms, deserts, ice, animals, intelligence, and wonder. As scientists scan the stars for another Earth, they are also helping us understand this one. And maybe that is the greatest discovery of all. The more we search the universe, the more extraordinary our own planet becomes.
This is infinite science. Keep looking up, because the next world we find may change everything.